Hello, this is Dr. Stephen Jones. This is part 2 of chapter 3 about decision analysis. We're going to take a look at topics such as decision making under risk, expected monetary value, decision trees, etc. So let's get started. First thing, expected monetary value. If you take a look at that option, really this looks very similar to something that we just did in the first video, where we were trying to sum the possible outcomes and the probabilities of those outcomes, because that's exactly what you do with that one. And as a measure of risk, remember from the last video where we said you could look at 50-50 or unknown risk, where you would create all the possible outcomes as equally likely, or if you were more optimistic or pessimistic about certain outcomes, you could assign them different values. Summing all those values with their possible summing all of those probabilities with those possible values then would give you certain valuations on each alternative, and then depending upon the level of risk aversion or liking to take risk, you might choose to maximize your maximum profit or maximize the minimum amounts of damage that you could take, or minimize the maximum amounts of damage you could take, and et cetera, et cetera, et cetera. And there's different options out there. So what else might you be taking a look at? If you wanted to minimize your risk, you might look for more information. And that information is going to cost you resources, time or money or both. And so how would you know whether or not to go looking for more information if you needed more to be able to make a better decision? Well, looking at that expected monetary value then, you would see that that type of approach works very well in looking also at the value of information. So an expected value of perfect information, getting as much as possible, should have an upper bound limit, or else you might just spend more money on that than you would actually have made profit-wise. And if you want to look at that long-term, getting more information and better alternatives long-term, not just on a one-time, then you're again looking at summing that up, and you can see the formula there to take a look at it. Expected opportunity loss is just one other face of expected monetary value and expected value of perfect information, trying to decide if you didn't choose the best solution, then what might you be losing out on. Opportunity loss is very similar to looking at what the expected values are and what your upper bound is for values of perfect information. So those are all intertwined, and when you create the equations to do one of them, you're really shining a light to do all of those out there. Now, decision trees are in the elm family. No, that's a joke. Decision trees do look like trees, I will tell you though, because they can branch out and branch out and branch out. And so each time you have a decision to make, you have nodes, and those lead to more possible branches and alternatives and expected values and probabilities and possibilities out there. So the more complex the decision, the more complex that decision tree is actually going to look. But it is a graphic representation rather than just a numerical table. We did take a look at options such as the expected monetary value and Maximax and Minimax and Maximin. That's really on a table, and we are turning that table into a tree to try to come up with best options out there. So in creating that decision analysis tree, again, you need to define your problem correctly, and if you've done that in a quantitative table or even just on a sheet of paper, you should be able to then find the starting point for what your decision tree is going to be. As you start to construct that decision tree, you first come up with what alternatives face you at the very start, what those probabilities are for each of those states of nature or outcome options that you have, what are the payoffs, sometimes profits, sometimes labor hours, sometimes other resources that are possible for each of those alternatives, and then you can look at the expected monetary value for each of those and try to use that as a decision tree. And remember, you have to have some idea of probability here and some idea of your alternatives and the outcomes related to those alternatives to be able to make a pretty rational decision tree. But this is the same thing that you would determine if you were trying to use a table for this. It's just going to be a graphical representation, and that's kind of what one looks like to start with. So you're going to go from left to right in a decision tree. You're going to have a decision that comes up and alternatives to that. And then there'll be values placed on each one. So for example, if you took a look at a decision node and then using the Thompson's decision that we went through in the last video about whether or not to construct a large plant for backyard sheds, you had three options: constructing a large plant, a small plant, or doing nothing. And if you take a look at it, if you choose to do nothing, notice there's not a node down here because you did nothing. So you wouldn't be doing anything. It's got a zero value to it. And that's what you saw in the table, but it's what you would see in this decision tree as well. If you have a large plant that you created, then you had the favorable market and unfavorable market were the states of nature that came along with that. And the same thing for constructing the small plant. Now, under that, as you see, you remember that you had an expected monetary value that would start coming out for each one of these. You had, if, let's say, you thought of the possibilities, remember the second one where you had no idea if it's a favorable or unfavorable market, then you gave equal weight to both of those, and the equal weight to the 200,000 and to the 180,000 had an overall average there of 10,000 for the expected monetary value for this node right here, whereas you had a 40,000 for this one, and again you had zero value to this one. And so if you wanted to do the expected monetary value with these probabilities, you would do this in a decision tree mode to where it looks graphically very much like this slide does here, as opposed to the table that we had when you were trying to calculate all kinds of possibilities for Maximax, Minimax, etc., etc., etc. However, you also have a possibility if you wanted to do a market survey or not. and that's looking for perfect information. See how much more complicated this gets now. You still have the situations where you have the large plant, the small plant, and no plant. But this comes off of the decision about favorability of results and what you think you're going to get out of it. This is not what actually happened. It is what you think is going to happen here. And so if you believe that 45% on that survey is going to be a 45% probability that your results are favorable, and then you take a look at the large plant, small plant, no plant options, and then the favorable markets and unfavorable markets out there, that starts to change. Notice, you, based upon what your survey results are, that's going to change what your probabilities are for these marketplaces as well. Okay, so if you didn't do a survey, you would still think it's a 50-50. If you did a survey and the results were favorable, that would change then under a favorable market and unfavorable market, because you already had a survey that told you you thought it was going to be favorable market. So the chances for a favorable market went from 50% now up to 78%, and unfavorable down to 22%. On the other hand, if you thought your survey results might come back negative, then that's going to drop the favorable market to 27%, and unfavorable would shoot up to 73%. And that's going to change all of these payoffs right out here, which means then your choice of what's the best option is also going to change out there. Now, if you have survey results, you do have to remember it's a survey. It's not perfect information. It's better information potentially if that survey was done properly, but you don't always know that that's going to happen. But it is at least more information, if not necessarily better information. And if you do get better information, then obviously it's a help to you in making a better decision at a later stage. Now, the idea of utility theory. If you remember in your economics, utils. Utility theory is that whole idea that there is a value to something, and money is not necessarily the only value that you have. It is one of the ways we make decisions, and it's a good way that we make decisions. Why? Because it is a relatively consistent way to value options and alternatives across different platforms. However, there may be other things that you also value. So customer goodwill, employee goodwill, community responsibility out there, ethics may also weigh in. Whereas a decision might potentially bring the most profit, it might also bring the highest chance of legal action or ethical improprieties, or you might have to fire a lot of employees and then you would lose goodwill. So there are a variety of things that may change the values that you put on things. Finally, this is a table that shows a graph that shows a little bit about people and their values for risk. It doesn't show how many people value risk or are risk averse, but rather it shows that people who are risk avoiders, those that are risk averse, would find more utility in monetary outcome as the risk has increased, would find more importance in the monetary values here, but that would start to flatten out. And at a point, the risk is too high, and monetary outcomes seem too risky for them. Whereas for risk seekers, unless the money gets really to be a good amount, that doesn't have that much utility to them. So risk seekers want to seek out that level of risk a little bit better, and so you need to crank that up. They're more likely to play high stakes poker. Risk avoiders are more likely to play low stakes. So if there's not much to lose, then hey, that's a great thing. But as you get more and more potential for loss at higher and higher levels, they tend to downplay that. People who are risk indifferent, they don't care about risk that much, then money and utility go together just fine. As it goes up, it is more important to them, but on a steady level, as opposed to it cranks up for risk seekers and flats out for risk avoiders. Okay, you should also watch the video where I talk about how to solve one of those problems like the Thompson's problem that we did. Talk to you later.